In this video, I want to go a little bit further into the study of differential equations, and let's say you have a differential equation that can be written in this form: a of x dy dx plus b of x times y equals c of x. Well, assuming this isn't separable, because this actually could be, what you could do to solve this kind of differential equation is you could divide out this a of x, and what you would end up with would be dy dx plus p of x times y equals q of x. And this right here is called a first order linear differential equation. So what exactly makes a differential equation linear? Well, it's the fact that this dy dx, which I have circled in red, is to the first power. It's not dy dx squared, it's not sine or cosine dy dx or log natural dy dx, it's just dy dx. So that right there is what makes this linear. And so, first of all, how would you then solve this kind of differential equation? Well, this one is actually very similar to an exact differential equation, and using the right integrating factor, we can even make this exact. So what would that look like then? Well, consider what I had mentioned earlier about a total differential. So if I had a function f of, let me actually write that down here. If I had some multivariable function f of x, y, I could incorporate the chain rule into this. Actually, I could write this potentially as a function f of x, y of x, if I could just define my second independent variable in terms of my first. And if I wanted to then take df dx, so my derivative of this with respect to x, I just wrote df df there. If I want to take df dx, my derivative of this function with respect to x, that would be equal to partial f with respect to x times partial y with respect to x dy dx. So hopefully you can see the chain rule characteristics right here. I had a function of x, a simple function of x, and I just differentiated it with respect to x, which is where I got this partial f with respect to x. And then I had a composite function with respect to x, so I took the outer derivative and I multiplied it by the inner derivative. So my outer derivative would have been partial y with respect to x, and my inner derivative would have been dy dx. All of this right here. And if you remember the chain rule from single variable calculus, dy dx is equal to dy du times du dx. And you could, if you wanted to make it simpler, look at it in terms of how these du's would cancel out, but that's really not the way it works in theory. But if you wanted to simplify that, then you could totally do that, and that works for any number of variables. So for any multivariable function, whether it's a function of 2, 3, or any infinite number of variables that the function can have, if you wanted to apply the chain rule. So with that being said, if I multiplied all of this times dx, I would get df equals partial f with respect to x times dx plus partial f with respect to y times dy. And that is a total differential of a function. So in case any of you guys are taking multivariable calculus, this could come in handy as useful information. At one point I knew what a total differential is. I didn't quite know how it related to the chain rule. It seemed a little bit sketchy to me, seemed maybe a little bit too theoretical, but that is how a total differential and the chain rule relate. And so this kind of differential equation, we'll be turning it into an exact differential equation. So we're also solving for some unknown function f of x, y, but we've got it set equal to something, this q of x. So here I have the generic form of a first-order linear differential equation, and the question remains, what function f of xy would satisfy this such that it becomes a total differential? And first thing I'm going to do actually is I'm going to multiply out my dx to make this a little bit more, I guess you could say a little bit more generic, a little bit more proofy in terms of being able to thoroughly explain everything. So dy plus p of x times y dx equals q of x times dx. And for this left hand side to be a total differential, I'm going to rewrite it actually, this p of x times y dx plus dy, which is equal to q of x times dx, so equals q of x dx. For this to be a total differential, we need partial m with respect to y to equal partial n with respect to x. And more than likely, it's pretty obvious that this probably is not the case. If I said m of x y equals p of x times y, and I said n of x y equals 1, well, partial m with respect to y would just be p of x, whereas partial n with respect to x would be 0. So this is not exact right now, but what if there was something I could multiply all of this by to make it exact? There is, and that's what's known as an integrating factor. And by doing it, I'm going to make this, by multiplying all of this by an integrating factor, I'm going to be able to turn this into an exact differential equation. So here I have the generic form of a first-order differential equation, of a first-order linear, more specifically, and consider this. If I multiplied all of this by some function e to the power of the integral of this p of x with respect to x, then I would turn this into a total differential. And in case any of you all don't quite see it, in case anybody doesn't quite notice the chain rule on this, let me write this down here. So I have e to the power of the integral of p of x dx times p of x times y dx plus e to the power of the integral of p of x with respect to x times dy equals e to the power of the integral again, e to the power of this integral times this function times dx times differential x. And so obviously I just said that this is a total differential, and in case anyone doesn't quite see it, if I said f of x, let me fix that x there. If I said f of x y equals e to the power of this integral times y, and I wanted to find the total differential of f, df would be equal to partial f with respect to x times dx plus partial f with respect to y times dy. So df in this case would be equal to, what's the partial of f with respect to x of this e to the p of x? Well, the derivative with respect to x of e to some function, say u of x, or in this case p of x, it'd be e to the power of that function, so e to this integral, e to the integral of p of x dx times the derivative of whatever e is being raised to. And in this case, since e is being raised to an integral, the derivative of the integral is just the function. So e to this integral times the function itself times p of x, and all of that would be multiplied by y, because that would have been a constant, and that would be what df is equal to, and then all of that times dx. And see, this partial f with respect to y, on the other hand, would just be equal to e to the power of p of x dx, because the y would be a constant. So that's this here that I have boxed in. This is the whole rationale behind why this method would then make this differential equation exact. So with that being said, now we have the total differential of the integrating factor e to the p of x dx times y, and that is equal to that's equal to e to the integral of p of x dx times q of x times dx. Don't get the dx's confused. And with that, we can integrate both sides. So the integral of a differential, what you do to one side, you must do to the other, but the integral of a differential is just going to be the function. So now I have e to the power of p of x dx times y, and I can't really simplify this here if I'm trying to do it in a very generic, proofy way, so I'm just going to go ahead and write this integral of e to the p of x dx times q of x. And so in conclusion, y equals the inverse of this, so e to the negative integral of p of x dx times this entire integral, e to the p of x dx times q of x. And this is the solution to the differential equation. I forgot to write a dx on this side here, but this right here is the total solution to this kind of differential equation.